Your staging environment looked perfect. Every API call returned in under 200 milliseconds. The LLM, that is, the large language model, the AI system predicting the next best token based on everything it has been trained on, responded cleanly. Your orchestration layer, the code responsible for deciding what the model calls and in what order, was moving data between services like clockwork. You shipped to production on a Thursday afternoon. By Saturday morning, your on-call engineer was staring at a cascade of timeouts. And the worst part? The model itself was fine. Your prompts were fine. Your infrastructure was fine. The failure lived somewhere most engineers never think to look. Inside the loop. So what actually happens inside an LLM orchestration loop? Not in the marketing diagram. Not in the quickstart notebook. In the real sequence of events that runs every time your production system tries to use an AI model to do something useful. That is what this video is about. Start with the simplest possible version of orchestration. You have a user request. You send it to a model. The model gives you an answer. That is a single-turn call. It is not an orchestration loop. It is barely an orchestration anything. Most production systems that matter are not doing this. They are doing something fundamentally different, and understanding why that difference exists is the first step to understanding what can go wrong. A real orchestration loop exists because a single model call cannot solve most production problems on its own. Think of it like a kitchen, a single chef reading a recipe once and plating a dish. That is your single-turn call. But a real restaurant kitchen has a head chef coordinating a prep cook, a line cook, and a plating station, each doing one thing well, passing results to the next station and sometimes looping back when something is wrong. The orchestration loop is that kitchen. The LLM is not the head chef. The LLM is usually the line cook, highly skilled at one task but dependent on the system around it to receive the right inputs and pass outputs to the right next step. So what does that system look like, step by step? It starts with a planner. The planner, sometimes called a router, sometimes an orchestrator, sometimes the outer agent, receives the raw user input and decides what needs to happen. In the React framework, which was introduced by Yao et al. In a 2022 paper from Princeton and Google Brain, this planning step is formalized as a reason-then-act loop. The model does not just answer. It first reasons about what tool to use, then acts by calling that tool, then observes the result, then reasons again. That cycle, reason, act, observe, is the heartbeat of most production LLM orchestration systems today. But the React loop is a pattern, not a guarantee. What actually happens inside your running system is a sequence of discrete function calls chained together by your orchestration framework, LangChain, Llama Index, a custom Python class, or increasingly a framework like LangGraph or Microsoft's AutoGen. Each of these frameworks wraps the same underlying mechanics: a call to the model API, a parser for the response, a dispatcher to route that response to the next action, and a memory object to hold context across turns. Here is where the first invisible failure mode lives. The model returns a response. Your orchestration layer passes it. But what the model returned and what your parser expected are not the same thing. Not because the model is broken, because the model is probabilistic. It does not follow your schema because you told it to. It follows your schema because, given everything in its context window, that was the most likely next sequence of tokens. And sometimes, under novel inputs, under context window pressure, under edge cases you did not test, the most likely tokens are not what you needed. This is schema drift. It is silent. It does not throw a 500 error. Your orchestration loop catches an output, tries to parse a tool call out of it, gets malformed JSON or a missing field, and then, depending on how your error handling is written, either retries blindly, skips the step silently, or crashes in a way that surfaces 6 layers up from where the actual failure happened. Pydantic, the Python validation library, is your first line of defense here. If every model output is immediately validated against a typed schema before it touches any downstream logic, you catch the drift at the source, not after it has propagated. The rule is simple. No raw model string should ever pass directly into a tool call, a database write, or a downstream API without going through a typed validator first. But